Moving to our next session, Ed Mitchard, co-founder and CTO at Space Intelligence, will be talking about leveraging space intelligence to fight climate change. Here's something so interesting that you don't know about Ed. He has measured the diameter of over 10,000 trees by hand in 13 different countries, mostly in the tropics. I'm super excited to hear his talk, and I invite you all to move to the next stage. Ed, over to you.
Hi, I'm Edward Mitchard. I'm the Chief Technology Officer of Space Intelligence. Thanks very much for joining me. I'm just going to share my screen. So I'm here to talk to you today about how satellite data can be used combined with artificial intelligence in order to fight and help combat climate change. So, as you may know, there are tens of thousands of satellites orbiting planet Earth at the moment. Over 1,000 of those are collecting what's known as Earth observation data. That is data about the Earth's surface. Most of those are taking what you'd consider as pictures. They're collecting optical data, but some are taking other types of data, which I will talk to later. One of the great things about this is almost all this data is easy to access. Lots of it is free of charge, provided by space agencies, funded by taxpayers, mostly in Europe and North America and Japan, and even lots of the commercial data is free for research purposes. So we're in a golden age of Earth observation with so much data ready to use. We're also in a time of big climate crisis, our burning of fossil fuels, but also by our destruction of the natural world. And satellite data is essential for helping to fight that. So example I have here, this is an image taken from an aircraft, in fact, of a small patch of deforestation in Peru. This is an illegal gold mine where the trees have been totally cleared and the ground churned up in order to filter through the mud for gold. This would be totally invisible to a boat going down that river. So a police boat would not be able to see this deforestation, even though it's maybe 100 meters away from the river. The only way to see this type of deforestation is looking down from above. Some deforestation is more obvious. This is an example from Indonesia where a hillside has been cleared for agriculture. Here's another one showing that process where forest is often thinned out for timber, then eventually totally cleared and converted to agriculture or other land uses. In this case, satellite imagery isn't really needed to show where that is happening. That's often very visible on the ground. But satellite data can still provide information on where forest restoration should happen and tracking the growth of that forest restoration, the enhancement of biomass as we restore the natural ecosystems that we may have destroyed. There's a lot of hope that there's international funding following the recent Glasgow Climate Pact for restoring landscapes as well as preventing deforestation. Hopefully money will start to flow to developing countries to help them to choose a cleaner developing path than we were able to in the West. I'm very supportive of that, and we hope that companies such as Space Intelligence will provide a funnel of data, of information that enables that transition, those funds to be used wisely to do restoration and forest protection. So I said I would introduce you to the types of satellite data. There's two major types, passive sensors, which are mostly optical sensors. These are effectively cameras on a satellite. They use the light from the sun, see what's reflected back, and use that to see what's going on. They can use the same wavelengths as we use with our eyes, so red, green, and blue, but they also often go further into the infrared, where the atmosphere is a bit more transparent and get additional information. They can't collect data at night, or at least only on kind of street lights and things, and they're limited by cloud cover. But these are the main types of sensor that collect data. The other type are active sensors. Rather than using the sun for their illumination, these sensors send pings of either microwave data or laser light at the ground surface and listen, if you like, for what comes back to the satellite. In case of radar, these are looking at the kind of three-dimensional roughness and the amount of water in the surface, so they can tell the difference between a small tree forest and a forest full of big trees, for example, which helps us track the carbon stored in forests. LiDAR sensors use laser to give a precise idea of the height of forests as well as the elevation of the ground surface, which can be very useful again for determining the biomass stored in forests and sometimes something about the biodiversity, the range of life that they support as well. And the whole Earth is imaged many times, often several times a day, by different types of sensors. We can build up these continuous observations into what's called a data cube. Lots of observations of the same place through a year, for example, or lots of different wavelengths of light or way of looking at the same place within only a few days. You end up with these big, rich data cubes, which contain a lot of information about the land surface, but they're quite hard for a human looking through them to get that information. There might be thousands of scenes, and they may have atmospheric contamination or clouds and so on. So what we do in space intelligence, and others do as well, is look at all of these together using the power of big data processing and AI to get something sensible out of these data sets. So here I have an example of a study area where we have a dense stack of optical satellite data from ESA's Sentinel-2 and a dense stack of radar data from ESA's Sentinel-1. Both cases, these are funded through the EU's Copernicus program, and they provide free and open data. We process some training data that might be about the carbon stored in this landscape in trees through going out and measuring the diameter of trees, or it might be something about the surface. So, for example, the location of intact and degraded forests. We build a machine learning algorithm, we test it using independent data, and end up with a model that we apply to produce an output. In this case, this is a map of where different land cover types are, so water, forest, degraded forest, agriculture, for example, and we can track how those are changing through time. That might help someone trying to set up a project to protect forest or restore forest, as I said initially. Now that's great, and that can be useful for conservation, but the other side of the coin that I wanted to consider today is that AI and storing these data sets fundamentally burns carbon. There's a lot of energy intensive work that goes on in turning these big data sets into output maps. This is something we're aware of, and you should all be aware of if you're running such models. There's a few ways in which you can reduce the environmental impact of your code. So you can look at the energy policy of data centers. We tend to use data centers that are only powered by renewable energy, wind and solar. That doesn't totally absolve you of all guilt, because clearly if you weren't running your code, some of that renewable energy could be used to offset and mean that a gas power station gets turned off. So that's necessary but not sufficient for reducing impact. You can test your code on small data cubes and optimize it rather than running big models and going, oh, have to do that again and again and again and burning a lot of carbon. If you're doing lots of runs overnight repeatedly on the same data sets, you're probably doing something wrong. You can run code like Code Carbon to look at different options for machine learning that you might have, see which one burns less carbon so that you can choose the better option. In all these cases, these are sensible decisions as well. They are normally it's cheaper to run your models fewer times, use fewer cores than you, and try and keep everything to the minimum that you need to do. So it's a sensible business decision to put some effort into choosing how to minimize the carbon impact of the AI you're running. Okay, my conclusion is that there's lots of unused potential from satellite data, loads of data being collected. It can be used to help save forests, target restoration forests, and probably many other things. We are focused on using it for nature-based solutions, and we will think this golden decade of Earth observation, hopefully this decade of ecosystem restoration, will be successful, and we're going to carry on providing satellite data to help solve the problems. Thanks very much for listening, and I think we've got time for some questions.
Well, thank you. Questions indeed. Let me start with space imagery or AI tools are becoming more accessible than ever before. How do you think this could help accelerate efforts to fight climate change?
Yeah, well, I hope I went through some of that in the talk. I really think that you can't have funded programs to reduce deforestation unless you have regular monitoring. No one is going to pay large amounts of money to reduce deforestation unless they have independent data they trust. That's only going to come from satellite data. So that's definitely a thing that will happen. But it's also about targeting these programs, these nature-based solutions. Again, you need satellite data, consistent views of the world to plan the best places to do restoration or avoided deforestation projects.
Mm-hmm. Yeah, you actually mentioned this like part in the presentation. How about the governments? We have a question on governments and how could governments and policymakers keep track of their CO2 footprint, and take actions to reduce it?
Okay, so all governments of the world are mandated under the UNFCCC to keep a track of their total carbon emissions. They mostly do that by following a set of standards they have to, as recommended by the IPCC. Those don't normally involve much satellite data at all, and often the numbers that come out of those disagree from satellite-based estimates of their carbon footprint. Some of that is due to the difficulties of how these things are calculated. Some is due to non-territorial emissions. So something that's made far away might not count as part of your emissions under some accounting methods and might on others. I think it's something that needs to change, and independent organizations will increasingly monitor what's really going on in countries and force them to act. An example of that would be Brazil, which has received a lot of negative press on the increase in deforestation that's happened there over the last few years. If it hadn't been for satellite data processing, we wouldn't know about that, and the pressures to change their policies from the international community just wouldn't have happened.
Okay, so I said we have one question. Someone is curious about how you came up with this and how you started working in this field.
Okay, yeah, it's a great question. So I was very interested in deforestation while I was at school, and I went to university and studied biology and got really interested in ecology, and particularly tropical ecology. But my university degree didn't include any analysis of satellite data or remote sensing. I really wanted to learn that, and I was lucky to get funding for a PhD at the University of Edinburgh, co-supervised by someone called Sasan Saatchi in the Jet Propulsion Laboratory in NASA in California. And that's where I learned how to use satellite data. So I did my PhD and then worked in academia in the University of Edinburgh for 10 years or so after my PhD. And I founded this company in 2017 with one of my colleagues there, because while I love academic research and training students and being at the cutting edge, we just wanted the tools that we'd already developed to be used more in the market to save actual forests. And that's much easier to do in a company providing services to other companies or governments than through the university, which is more geared to research.
Wonderful. This has been really inspiring. Thank you so much, Ed, for joining us.
Thank you.